Ladies and gentlemen, we've completed the chapter now on transient heat conduction, and today we are going to start with chapter 6 in the textbook of Cengel and Ghajar, and that is the chapter on the fundamentals of convection. Chapter 6, paragraph 6.1 is the physical mechanism of conduction, and just trying to explain it to you, let's just go back to what you've learned so far in heat transfer. You've learned that there are three different modes of heat transfer: conduction, convection, and radiation. Right, conduction is chapters 1 to 4. It is steady state conduction, the first three chapters, and then transient heat conduction in chapter 4. Now there's going to be actually quite a number of chapters on convection, and then there are 2 chapters on radiation. As soon as Dr. Leroux is finished with that fluid mechanics part of the lecture that he's busy with, he will continue with the radiation part while I will continue with the convection part. So what are some of the differences with these 3 different modes of heat transfer? Well, the first one is that normally with conduction it occurs in solids, and it can also occur in fluids and gases. If velocity is equal to 0, and I'm going to explain that just now. With convection requires fluid motion. Thus, the velocity, okay, I shouldn't have done that, sorry, because we've used that V for volume. So it should just be a normal V. If that is larger than 0, then we will have convection heat transfer. And these 2 modes, not radiation, requires the presence of a medium. Radiation heat transfer doesn't require a medium. It can radiate right through a vacuum, no medium, but these 2 requires a medium. Conduction heat transfer normally in solids, but it can also occur in fluids and gases in very special cases, and I will explain it to you just now. Convection heat transfer is normally where there's a motion of one other medium, and normally the medium would be a fluid and or a gas. So, trying to show it with an illustration, let's suppose we've got a flat plate, and this flat plate is at the temperature of 50 degrees Celsius, and we've got a fan, and this fan would force air at a temperature of 20 degrees Celsius and a velocity of 5 meters per second over the flat plate. There will then be heat transfer from the plate to the air, and I'm going to show it as Q.1 because it's the first mode of heat transfer, and we're going to call that forced convection. Okay. So the air is being forced over the flat plate. It doesn't always have to be a fan. It can also be a pump or any pressure difference between 2 points. Will cause a heat transfer, which we call a convection heat transfer, which we call forced convection. The second type is, again, we've got this flat plate, the temperature of 50 degrees Celsius, and now we've got air at 20 degrees Celsius, but the air is not being forced over the flat plate. This air at 20 degrees Celsius will touch the flat plate the temperature of the air will increase, and that will cause a buoyancy force. So the air close to the plate is going to do something like that. So there will be a velocity on this flat plate. It just would be very, very small. So the velocities are small. And this we're going to call natural convection or free convection. Natural convection or free convection. So forced convection, the velocities are quite large, and with free convection, almost zero, but not zero, just very small. Natural convection. And the third mode of heat transfer is then where we've got this flat plate. Again, there's a temperature of 50 degrees Celsius, but where previously we had gravity working in this direction, the gravity would be equal to zero. Okay, so gravity is equal to zero. If that is the case, then, okay, so that would be the heat transfer mode, would be the heat transfer Q dot 2, and in this case it would be Q dot 3. There will also be heat transfer, but now the heat transfer would be through conduction. So that is the special case where a fluid and or a gas, there will be heat transfer, will be conduction, because even although these gas particles or air particles will be heated, they cannot just move up because of the buoyancy forces, because gravity is equal to zero. Okay. Now, in general, convection would cause an enhancement in heat transfer. Enhancement in HT, heat transfer enhancement. Why? Because it would bring together the fluid particles which has been heated and the ones who hasn't been heated yet, the colder ones, and it would actually help and enhance the heat transfer rate in the medium. In general, the convection heat transfer rate is a function of quite a number of things. Firstly, of the fluid properties. And the fluid properties that will influence the convection heat transfer will be the viscosity, the thermal conductivity, the Cp value, the density value, and the Cp value. That is the first thing that will have a huge influence on the convection heat transfer rate. The second thing that will influence it would be the fluid velocity. The fluid velocity V. The third thing would be the geometry. The geometry. In the previous example that I've showed here, we had a flat plate. So it can be a flat plate like that, or it can be an aerofoil with external flow around the aerofoil, or it can be in a circular tube or in a square tube. Any different geometry, all the different geometries will affect the convection heat transfer. Then it will also be influenced by the surface roughness. The surface roughness would also influence it. And then lastly, the type of fluid, the type of flow. And with the type of flow, we mean the flow can be in the laminar flow regime, it can be in the transitional flow regime, or in the turbulent flow regime. All of that will have an effect on the convection heat transfer. So because of this, convection heat transfer is a very complicated field. And there's a Nobel Prize for anybody who can figure out how to write the convection heat transfer as a function of all those properties. Okay. But since nobody has won the Nobel Prize yet, we still make use of Newton's cooling law, which says that the convection flux is equal to the heat transfer rate divided by the surface area. There's a question.
I just see you wrote CP value there twice. I don't know if you might have made some other value.
Thank you. Yeah. CP. I think it's all of them, fluid properties. Okay. Okay. So the convection heat transfer, this is a flux, this is the heat transfer rate per square meter, is equal to the heat transfer coefficient multiplied by Ts minus T infinite, and the units is in watts per square meter, the heat flux. But the very important thing is that all these complications is actually put in that value there. So because we don't know what this influence is, this functional influence, we jippo it with the heat transfer coefficient. Okay. So this is the heat transfer coefficient, this is Newton's law. You can also write it, in the beginning maybe you're not going to like this heat flux. You can also write it, of course, as the convection heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area Ts minus T infinite. Ts, the temperature of the surface, T infinite is the free stream temperature, and then the units is in watts. So this H, we are going to call it the heat transfer coefficient. And I'm going to, in many cases, just refer to it as, no, wait, let me not do that, sorry. Okay, so H is the heat transfer coefficient, and its units is watts per square meter degrees Celsius, or watts per square meter Kelvin. Just coming back to what I've mentioned previously, let's suppose the heat transfer rate is 1,000, the heat transfer coefficient is 20, the surface area is 1, and your temperature difference is in terms of degrees Celsius. Okay, then you can write the heat transfer coefficient as watts per square meter degrees Celsius, the value that you're going to solve. However, you can also write it as temperatures in Kelvin, because the temperature difference in degrees Celsius and Kelvin is the same. This unit can also be written as watts per square meter Kelvin. The values would be exactly the same. So you will see that both these formats are being used in the textbook. Going back to fluid mechanics, we're going to go back quite a lot in fluid mechanics in this chapter. I'm not going to revise everything, I'm just going to refer to it, and it would be good if you can just go and read through it again. But going back to the no-slip condition that you've done in fluid mechanics. So in fluid mechanics, you've looked at an object. Let's suppose it is an aeroplane aerofoil, and this is the free stream velocity, V infinite, and you would go and measure the velocity here somewhere on the wall. Then there will be a velocity distribution that would be V infinite, the free stream velocity, but as you go closer to the surface, you will get to the point where that is called the no-slip condition. The no-slip condition, and that would be where the velocity is equal to 0. And at that point, if we use the coordinate system y and x, okay, I will come back to the coordinate system just now, y and x. So that is what you've learned in fluid mechanics. With heat transfer, we've got something very similar, and that is that if this is the temperature distribution, let me use a pink color to show the temperature. It's not a vector, let's just show it as this, like that. Okay. Then the temperature there, at that point there, would be Ts, if that is the temperature of the surface, and that is T infinite. So the no-slip boundary condition, which is being used in fluid mechanics, where the velocity on the wall is equal to 0, at that point the temperature would also be the temperature of the solid. Right, now for that reason, if we go back to this equation, and that is equation 6.1 in your textbook, then we can actually write that the convection heat transfer rate is equal to the conduction heat transfer rate is equal to minus K of the fluid partial dt dx, where y is equal to 0. And that's equation 6.3 in your textbook. Thus, here on the boundary, although this is our convection heat transfer, on the boundary, the mechanism of heat transfer is conduction from the solid to the fluid. That is equal to conduction. And if we equate equations 6.1 to 6.3, then you can actually solve that the heat transfer coefficient is equal to minus K of the fluid multiplied by partial dt dy, where y is equal to 0, divided by Ts minus T infinite. This therefore means that we need to know what is the temperature profile at this point to know what the heat transfer coefficient is. Okay. Now in your textbook there is an example where the temperature distribution is given and you have to calculate the heat transfer coefficient. However, in practice we never do it like that. We do it differently. We're doing it with experiments. But theoretically, if you know the temperature distribution here in the boundary layer, then you can go and determine the heat transfer coefficient for it. Now the heat transfer coefficient is very closely related to what we call the Nusselt number. The Nusselt number. And the Nusselt number, the definition of it is equal to the heat transfer coefficient multiplied by characteristic length divided by K. This LC is not equal to the volume divided by surface area as for lump system. Okay? So do not go and do it. Don't go and calculate it from the volume divided by the area. It is one or other characteristic length which has normally been used when the experiments were conducted. Okay. Now let me illustrate it by showing a layer of fluid, a fluid layer, which is at the temperature T2 and T1. The heat transfer rate would be from the higher temperature to the lower temperature. So here's the fluid layer, like that. And let's call that the y-axis in that direction and x in that direction. And then we can write that the convection heat transfer is equal to the heat transfer coefficient multiplied by T2 minus T1, the convection heat transfer. The conduction heat transfer would be equal to K dt dy, you remember, for conduction heat transfer, minus K dt dx or dt dy. I'm throwing away the minus sign because in heat transfer we sort of always know the direction of the heat transfer, so it's not a big issue. So we can write it as K multiplied by T2 minus T1 divided by L. And this is the distance L. Now where do I want to go with this? I want to show you that if we now look at the convection heat transfer divided by the conduction heat transfer, so the heat transfer coefficient T2 minus T1 divided by K T2 minus T1 multiplied by L, then it is equal to HL divided by K. Why did I do that? Because I want to show you that the heat transfer coefficient, the Nusselt number, which is equal to the heat transfer coefficient multiplied by characteristic length divided by K, is equal to the heat transfer coefficient. The characteristic length in this case was the distance between the two plates divided by the K. So we've got the same equation. What does it mean? It means that this equation, the Nusselt number, tells us how much enhancement we will have in comparison with conduction heat transfer as a reference. That is what it means. So the Nusselt number is the enhancement of heat transfer relative to conduction heat transfer. Thus, if we now look at those three cases that we previously had, the case where we had the fan, then where there was no fan, and then lastly, when G was equal to 0. So that was the case of forced convection, this was the case of natural convection, and that was the case of conduction only. Okay. So if we look at the case of conduction only, ratio of convection to conduction, it would mean that this is the case where the Nusselt number is equal to 1. Okay. With natural convection, there will be an enhancement of the convection heat transfer. The convection heat transfer will enhance the conduction heat transfer, and normally the Nusselt numbers would there be in the order of magnitude of about 10 to 20, order of magnitude 10. When we get to forced convection, order of magnitude 100 to 1,000. Nusselt number is how has the heat transfer been improved or enhanced. Therefore, and that can happen very easily with you, you're going to have very fancy and complicated equations in which you have to calculate the Nusselt number. And all of us can make an error. And you can end up with a situation where you calculate a Nusselt number of 0.8. The red lights should go on. Why? Because a Nusselt number cannot be smaller than 1. 1 is the smallest. 1 represents conduction heat transfer. So Nusselt number equal to 1 is the smallest possible Nusselt number. Are you all with me? Any questions on that? Okay, now paragraph 6.2 in your textbook, I'm not going to do in detail because you've already done it in fluid mechanics. It is just a revision of viscous versus inviscous flow. What was viscous flow again? Viscous flow is where the viscosity is not equal to 0. Inviscous flow were the cases where you assumed that the viscosity was very, very low or approximately equal to 0. Okay, just going to read it again. Internal flow versus external flow. Internal flow is flow through ducts, engines, etc. External flow is the flow that goes around an aircraft or around a boat. Compressible versus incompressible flow. Can you remember when is the flow compressible? Flow is compressible when the Mach number is larger than 0.3. Okay, the Mach number is larger than 0.3. How do we determine the Mach number? The velocity divided by the velocity of sound. You remember? Okay. Normally, water always incompressible. You should see it, I think you've already done it in thermodynamics, and that would also be the assumption that we will make in this course in most cases. Then, laminar versus turbulent flow. Who can tell me what's the difference between laminar and turbulent flow? Laminar flow is when you've got low velocities over a certain body, like maybe an aeroplane wing, and it would go in laminars, in layers. That is what laminar means. So if we measure the velocity as a function of time, then it would be a straight line like that. Even with the best instrument, it would be a constant. If it's turbulent flow, what will then happen? It will be at a larger velocity, maybe there. The average, if we measure it there, would be constant, but we will have fluctuations around this average. Okay. You remember? That's the difference between laminar flow and turbulent flow. When does the flow change from laminar to turbulent? Who can tell me that? When will you know if the flow is going to be laminar or turbulent? If the Reynolds number is equal to? Reynolds number is equal to? Somebody said something? 1,000, but it depends on? Fluid properties, almost. What is the value? Well, there's no general value for all bodies. That's the very important thing. So for an aeroplane wing, it can be a few 100,000. The Reynolds number can be a few 100,000. And the properties will already be in the Reynolds number, specifically the viscosity and the density. For a tube, it would be a Reynolds number of about 2,100 to 2,300. So the Reynolds number can be used, what we call the critical Reynolds number, as a criteria to distinguish between laminar flow and turbulent flow. However, it is not 2,300 for all bodies. It depends on the geometry. For a tube or a pipe, 2,100 to 2,300. For an aeroplane wing, it can be 1,000,000. It depends. Then, steady versus unsteady flow. What is the difference between steady flow and unsteady flow? This would be steady flow. The velocity doesn't change as a function of time. Unsteady flow would be when you've got something like that. Okay. It changes as a function of time. Okay. What is a good example of that? A good example would be a gas turbine of an engine. Okay, here, first part you've got the compressor, then you've got the combustion chamber, and then the turbine. And if you would go and measure typically the average velocity or the pressure at a specific point, it will be like that if the aeroplane is cruising at a constant velocity. However, if it decreases its speed to come in for landing, this velocity and pressure is going to change. Okay. The other change would be if there's a bird or something going through that turbine. Okay. Then you're not going to have something like that. Then it's going to change very quickly as a function of time. So the pressure and the temperatures and the velocities are changing as a function of time. Right, so that is paragraph 6.2, classifications of fluid flow. You've already done it in fluid mechanics. Paragraph 6.3, you've also done, but I would like to revise it because it is so similar to the paragraph that follows, 6.3. Okay. So 6.3, paragraph 6.3 is the velocity boundary layer. Velocity boundary layer. The best is to illustrate it on a flat plate. This is a flat plate. And our coordinate system is y and x in that direction. And we've got a free stream velocity coming in, which is uniform, which we're going to call V infinite. The no-slip boundary condition tells us that at this point here, this velocity is going to change from whenever it was to a value of 0. It therefore means that we've got a boundary layer which is going to develop like this, something like that, 3 different parts. The first part we're going to call the laminar boundary layer, then the transitional boundary layer and the turbulent boundary layer. To distinguish between the next section, I would like to make this in blue, like that, to indicate the velocity. And this blue line is the boundary layer thickness, lambda. That is the boundary layer thickness, like that. How do we determine the boundary layer thickness? Well, firstly, by looking at the velocity profiles. Okay. If we look at this velocity profile, and I'm going to enlarge it, then near the wall, it is going to do something like that. Let's suppose this velocity is 100 meters per second. Okay. Then, if we go far away from this flat plate, then the velocity would also be 100 meters per second somewhere far away from the plate. If we go closer and closer and closer and get to the point where the velocity boundary layer is 99 meters per second, then we define that distance as the boundary layer height, lambda. That's the boundary layer height. So that point there would represent the boundary layer height, and that is where the velocity, u is now the velocity as a function of y, where uy is equal to 99% of the free stream velocity. So 99% of the free stream velocity is defined as the boundary layer height. The characteristics of the boundary layer is going to be something like that in the laminar flow regime, while in the turbulent flow regime, it's going to look a little bit different. It's going to be more something like that. But again, if that velocity is 100 meters per second and we go down and down and down until we get the velocity of 99 meters per second, then that would be the boundary layer height. So there it is going to be 98, 97, 90, 80, 50, etc. up to 0. Okay, I want to do another sketch next to the velocity boundary layer. So before I do that, there are a few things that I first have to define and revise with you. And that is the wall shear stress. You've done it in fluid mechanics. We are going to use it in this module. So therefore just want to revise it. The wall shear stress is tau, and that is equal to the viscosity multiplied by du dy, where y is equal to 0. So where y is equal to 0, it means that gradient of the velocity boundary layer multiplied by the viscosity. And the units of it would be newtons per square meter. Now in general, in mechanical engineering, this equation is always valid. It is called, or it is valid for a Newtonian fluid, but there are also non-Newtonian fluids, and examples are blood and liquid plastics. For them, you need to use more complicated equations than this one. So this is for a Newtonian fluid. In general, if you go and look at viscosity as a function of temperature, you will see that viscosity is a function of temperature. For gases, it will actually increase, while for liquids, it will decrease in general. If you go and plot any liquid and or gas in your textbook as a function of time, you will see, as a function of temperature, you will see there is a functional relationship. In many cases in heat transfer, we work with temperature differences which might be very moderate. In most heat exchangers, temperature differences can be as small as 10 degrees Celsius. And if you go and look at 10 degrees Celsius, then you will see in most cases that would represent 10 degrees Celsius, and the viscosity for all practical purposes would be a constant. Not always, but in many cases. Okay, so that is the viscosity. We also call it the dynamic viscosity. The dynamic viscosity, and its units is kilograms per meter second, something like that. But then we also have the other viscosity, which is this one, which is the dynamic viscosity divided by the density, and this is called the kinematic one, the kinematic viscosity, and its units are pascals, its units is square meters per second. These units can also be written as pascals per second. The kinematic viscosity, why do we use it in many cases? Because it takes two of the properties. If we go and look at the heat transfer coefficient, which is a function of properties, it will take these two properties in one. So that is the advantage of using the kinematic viscosity. So that is why we're going to use it in some cases. Right, so as I've said previously, to get this velocity distribution is really not practical. To go and measure in a boundary layer, you will disturb it in most cases if you try to do it, so it doesn't work that well. So for that reason, what we normally do is we write also the shear stress as equal to Cf multiplied by rho v squared divided by 2. And where Cf is now called the friction coefficient. The friction coefficient, or the skin friction coefficient. Skin friction coefficient. And this skin friction coefficient can be determined for any body. And if we do it typically for an aeroplane, we would typically maybe use the free stream velocity for that specific geometry. or if it is for another type of geometry like that, then we would use that velocity and determine that, but it would be related to a specific geometry. Why is that important? Because we can use that to determine the friction force, which is equal to Cf multiplied by the surface area rho v squared divided by 2. So if we've got this friction coefficient and we use that surface area, multiplied that with the surface area, the friction coefficient multiplied by rho v squared divided by 2, we get the friction force. Friction force or the friction drag. Okay, so that was just a little bit of revision of your fluid mechanics. Now we want to relate it to heat transfer, to paragraph 6.4, which is the thermal boundary layer. Now with the thermal boundary layer, we're going to have something very similar than that of the velocity boundary layer. Thus, in that same fluid, if we have a certain free stream temperature, remember, temperature is not a vector, so that distance would just represent the temperature in degrees Celsius. So that would be its temperature. And now, also, we're going to have exactly these three same regions. And that is going to be called the thermal boundary layer, delta T, where that one is the velocity boundary layer. But what is going to be different, and let me draw it on this side. Okay, so that is going to be delta T. If we now look at the temperature there on the flat plate, what is it going to be? If we have to draw it. Well, where it's different now is that it is not zero. Or in some cases it can be. But if this flat plate is at 20 degrees Celsius and that at 0, then the temperature here is going to be 20, not 0. So therefore it looks a little bit different. I'm going to explain it to you just now, but it is going to do something like that. So that distance is the temperature. Okay. Like that. And let's do it with an example that normally helps. Let's suppose that temperature is 100. And this temperature is equal to 20 of the flat plate. How are we going to determine the temperature? Is we're going to say it is equal to Ts plus 0.99 times T infinite minus Ts. Now the 0.99 would immediately give you an indication that, you know, we are almost trying to do the same as with the boundary layer thickness, but it looks a little bit more complicated. It is not really. I'm going to do two examples for you that's going to illustrate it. So let's suppose it is 20 degrees Celsius Ts. Ts is 20. Then the temperature is going to be the temperature of the surface, which is 20, plus 0.99 multiplied by 100 minus 20. And that is going to be 20 plus 0.99 multiplied by 80, and that is going to be at a temperature of 99.2 degrees Celsius. So that value there is going to be 20. That one there is going to be 99.2, and the temperature just higher than that is going to be 100 degrees Celsius. Now that example doesn't really show it very well, but let's look at the case where the temperature of the plate is equal to 0. So if the temperature of the plate is equal to 0, then the temperature is equal to Ts, which is 0, plus 0.99 multiplied by T infinite, which is 100 minus 0, and that is equal to 99 degrees Celsius. You see? It's the same principle. It's 99% of the temperature distance, and that would be called the thermal boundary layer. Now, although I've got two sketches now, in the next part of the work, we are going to look at these two boundary layers and how they differ. So you can get a case where the thermal boundary layer is doing that. Okay? Not the thermal boundary layer, the velocity boundary layer. While the thermal boundary layer is going to be there. They're not going to be the same thickness. And there will be three conditions. We're going to look at three different scenarios. The first one is where the two is going to be exactly the same. And that will be where the Prandtl number, and I'm going to define the Prandtl number in the next lecture, is going to be equal to 1. And then you're going to have the case where the Prandtl number is smaller than 1. Is that important? Yes, it is important because all gases normally have Prandtl numbers smaller than 1. And then the other scenario would be where the Prandtl number is larger than 1. Is that important? Yes, because all liquids normally have Prandtl numbers larger than 1. And we will consider that in the next lecture. Any questions, ladies and gentlemen? If not, thank you very much.